Okay, so since we've got your test turned in, okay, so what I want to talk about next is we're going to be using some formulas. These are formulas that you've probably seen, but you've seen probably approximated formulas. So we're going to be looking at the exact version of them so you can see where the formulas come from. We want to talk about cutting speeds. So cutting speed is literally, of course, the speed that the tool moves across the surface of the material. If you think of it like this, if you have the tool, it would be, if you thought of the tool as a car or something moving across, it is that speed that the tool advances across the material. Now, sometimes it is the tool itself that's moving, sometimes it's the material that's moving. If this is a lathe, of course, the material is moving and the tool is stationary. If it is a mill, yeah, it's the tool that's moving, the material is stationary, and of course there's teeth on that tool that cut in. That's really ugly, but you get the point. Now, one thing that we are not going to consider in this class for a mill is we're not going to consider the number of teeth. You guys do a chip load and stuff like that. We're just going to do a feed rate when we get to that point. Conveniently, both a lathe and a mill involve something that's rotating, so the math ends up being the same. The distance moved of course, the relative distance between the tool and the surface of the material is found by taking the circumference of the material which that's just the distance for one rotation, right? Times RPM, how many times it rotates. And we're looking at distance moved, I could label that in 1 minute. Speed is just distance divided by time it takes to move that distance. So since RPM is revolutions per minute, our unit of time we're going to be looking at is going to be minutes. 1 minute. So we want to look at what's the distance this moves in minutes. Now, surface cutting speed what units do you use there? Feet per minute. It's in feet per minute. So finding that distance, that relative distance is our first step. We need to find that relative distance in feet, first of all. But let's start out. We have a diameter either of the material that's turning in a lathe or the diameter of the tool in a mill. The circumference is going to be pi times that diameter. So in either case, whether it's the material spinning in the lathe or the tool spinning in the mill, the circumference is pi times the diameter, whether it's the diameter of the material or the diameter of the tool. And then, of course, times RPM, we're going to use N to represent the number of RPM. What unit, however, is your diameter usually given in? Inches. Surface cutting speed is in feet. Divided by 12. And that is the formula right there, cutting speed, C, in feet per minute, is equal to pi times the diameter of the material times your RPMs divided by 12 to turn it into feet. So let's say we have a 5/8 inch mill turning 400 RPM. Its surface cutting speed, I'm going to put it in as 3.14 times, what's the diameter? 5/8. What's N? 400. And of course, divided by 12. 3.14 times 5/8 times 400 divided by 12. We get 65.42 feet per minute is our surface cutting speed. That's actually pretty slow. Most of your materials are up around 100, 120, aren't they? I've got the table. I never have them memorized. Now, obviously, this formula probably does not look like the one you use in the shop. So most of the time, what they use in the shop is they combine pi and 12. And they actually do it the other opposite way. What is 12 divided by pi? 3.82. So in the shop, often they just do diameter times RPM over 3.82. Yep. Okay. That's the same thing. They just divided out the pi and the 12, and they just use that consistently. That works exactly. Yeah. And I know a lot of people do use that before. But if you ever want to be more precise and you can't remember the 3.82, that's it right there. Just 12 divided by pi. You got to do it backwards because we're putting it on bottom. So it's 12 divided by pi, not pi divided by 12. So let's say you have 2-inch material in a lathe turning 350 RPM. In your notes, find that surface cutting speed for me. So our cutting speed, I'm just going to go ahead and use the shortcut. So we've got the 2-inch diameter times 350 RPM over 3.82. That's it, 183.25 feet per minute. You might have used pi. Just round off errors. Obviously, you're going to round these off anyway at some point. Normally, you're not given a setup and you're asked to find the cutting, unless you're double checking a program where the program is set to run certain RPMs. You calculate the cutting speed and compare it to a chart to see if it's at an acceptable speed. But most of the time, you're going to be the one setting the RPM, and you need to try to figure out how many RPM you're going to run it at. So your cutting speed, pi dn over 12. Most of the time, what you're looking for is this number right here. How many RPM should I run it at? Well, if you remember last semester, we arranged formulas like this. We did it by, we would multiply by 12 to get rid of that dividing by 12 there. Multiplying by 12 over here gives us 12C. And now we have to get rid of the pi d here. The pi and d, those are multiplying the ends. We're going to divide by pi d. Dividing by pi and d over here just gives us 12C over pi times diameter. That is our number of RPMs. So let's say we have 1.5-inch diameter material in a lathe. It is currently, let's see what type of, this is a stainless steel. And we're using a carbide tool. So you look that up, stainless steel, carbide tool, turning. It says you can run up to 200 feet per minute. Or as low as 60 feet per minute. So you pick a number in there somewhere in that range. Let's say we want to go quickly, we want to produce, but we don't want to push it too far. So let's say we're going to go 175 feet per minute. That's our target cutting speed that we're going to shoot for. So in our formula here, N equals 12 times C, 12 times 175, divided by 3.14. 3.14 times my diameter of 1.5. So 12 times 175. Now here's where it gets tricky. Divided by, I've got to put this in parentheses down here. 3.14 times 1.5. I'm going to do 1.5 and then close my parentheses. It will, yeah, if you don't close the parentheses, it'll divide by the 3.14. But then I'll multiply the top by 1.5. So I get 445.86. And that is RPM. Depending on which way I want my safety margins, if I'd rather be a little slow than a little fast, I might round it down to 440. Since I already had my speed tuned down a little bit, I may round that up to 450 and still be safe. I might have a 3/4 inch high-speed steel mill. I don't think you don't have too many mills down there that aren't carbide, do you? They're just the high speed? Okay. And we are going to do, let's say we're turning brass, we're milling brass. So we take a look for milling and brass, high-speed steel gives us a range. For brass, it's always a huge range. Anywhere from 250 to 450. Of course, that's feet per minute. So let's pick a number in there that we want to run at. 350 is our target, okay? So let's set this up. Our RPM, which is going to be N, equals. Now I'm going to do this short. I'm going to take that 12 divided by pi, which is 3.82. And I'm just going to put that in there on top. Times my cutting speed of 350 divided by my 3/4 inch diameter. So this is going to be 3.82 times 350 divided by. Now, since that's a fraction, I know a 3/4 of an inch is 0.75. I could just type that in. But if it were like 5/8 or 7/16 or some weird fraction that I don't, I mean, I know most of those offhand too, but if you don't know it off the top of your head, here's all you have to do is put it in parentheses, 3 divided by 4 and close the parentheses. That's 3/4. And I get 1782.67. Is my RPM. So again, we might round that down to 1700, might round it up to 1800, maybe 1750, whatever. It's, we're going to get to that. Hang on. Drilling is also looking at a rotating tool. So, yeah, whether it's a mill or whatever, it's still a drill is still a spinning tool. Let's see. So you got a 1/2-inch drill. Now let's do a 1/2-inch carbide. Actually, no, we don't have the chart for carbide. It's a 1/2-inch high-speed steel. Drill. And we're looking at drilling carbon steel. So carbon steel, it says we are allowed 70 feet per minute. So our RPM, I'm going to use the 3.82 again, times my 70 divided by 1/2. Now again, I know 1/2 is 0.5. I could do it as 0.5, but just so I keep modeling how to do the fractions, do 3.82 times the 70 divided by, then parentheses, 1 divided by 2 for the 1/2, and close the parentheses. So 534.8 RPM. Okay. The next step in all this is that feed rate. We'll get to that in a second. I do want to talk a little bit about metric cutting speed. You know, in my lifetime, we will see the conversion to metric. It's just I mean, everybody thought we were going to make the conversion by the early 90s, but we dropped it. In that mid to late 80s, everybody was gung-ho. We were making that conversion, and it just kind of faded. That was part of it, but in the last 4, 5, 6 years, a lot of major companies that do business internationally have said we're doing everything metric, domestic and out of country. In like IBM, they figured they saved like $8 million the first year they did that. Just because the design time of having to design everything in dual units and the time of having to convert tooling, if you send it out to be done at a foreign place, you've got to use different tooling and all that stuff. Having everything done in metric meant it was the same tooling, all one drawing, you didn't have to double label anything. And also, because you weren't converting units, there wasn't round off errors, their quality of the parts meshing was a lot better. They had a lot fewer rejects because parts didn't want to mesh. Well, and to be honest, that's why we kind of turned away from it in the late 80s and early 90s. Is you look at who's in power, who are your CEOs of major corporations, you don't see too many 40-year-old CEOs. They're mostly late 50s to early mid-70s. Those guys didn't learn the metric system when they were in high school. My generation was really the first generation to learn the metric system in high school. Starting in the late 70s, early 80s was when they started doing the metric system. So, and I'd say in about 15 to 20 more years, there's going to be that change in power to where people that are in those power positions are a little bit more familiar with the metric system. And so the transition will happen faster. Right now, we've left it up to government agencies. In the United States, you cannot buy a pound of gunpowder. You cannot buy a quart of alcohol. And you cannot buy a pound of tobacco. Anything regulated by the ATF, alcohol, tobacco, and firearms, is required to be bought and sold in metric units. That's why you go to the liquor store and it's a 0.75 liter bottle. Or you go to buy gunpowder, it's a 0.5 kilogram keg. Yeah. It's supposed, and it can be dual labeled. Like, you look at your bottle of soda or whatever, it says 20 fluid ounces, and then in parentheses it says however many milliliters or whatever. For gunpowder, it'll be the other way. It should be the metric. The kilograms or grams first, and then the pounds will be in parentheses. The main unit must be metric, unless it's an old. But if you just bought it, it should be set up that way. Yeah. But I mean, it's been 6 or 7 years that's been a requirement. I'd say the next government, and that's what the United States government has done, is they left it up to government agencies. I'd say the next one to go is going to be the FDA, because all your food is already labeled in both fluid ounces and milliliters, and all your nutritional information is already in grams and milligrams. Right now it comes as 32-ounce bottles. You've already seen like the 20-ounce bottles. There's the 16.9-ounce bottles for soda. That's the half liter. Yep. Yeah, they're already starting to make that change. You'll see it's 16.9 ounces, but that's a 0.5 liter is what it is. So yeah, they will probably change some of them over. Just like your 0.75 liter bottle of whiskey is not a fifth of whiskey. It's a little bit smaller, actually. So anyway, for metric cutting speed, it's still your pi times your diameter times your RPM. But now in this case, your diameter is usually measured in millimeters. And we need to convert it into meters. Cutting speed is going to be in meters per minute. What's the conversion between millimeters and meters? How many millimeters are in a meter? 1,000. So it's divided by 1,000. So if you have an 18 millimeter tool, mill, and we're, let's say spinning at 500 RPM. Your cutting speed is going to be pi times 18 times 500 divided by 1,000. It's going to give us 28.26 meters per minute. Now remember, a meter is a little bit more than 3 feet, so that's looking at probably somewhere around 80 to 90 feet per minute. Let's talk about that feed rate. Now, feed rate is how fast the tool can advance through the material or into the material. You guys do that chip rate, which it's a, let's say you've got a mill with 2 teeth on it. Each tooth can take a certain depth per cut, right? So you would have your chip rate times your number of teeth. That gives you your feed rate, which is in inches per revolution. So what we're going to do is we're going to assume when we say feed rate, that is already after considering teeth and chip rate. So that feed rate comes from taking the chip rate times the number of teeth. We're not going to bother with that. We're just going to say, hey, you found the feed rate, you did your chip rate times your teeth, and this is the number you got. A typical feed rate might be 0.003 of an inch per revolution, depending on your material. So let's say you are allowed a feed rate of 0.003 of an inch per revolution. If your RPM is 400 RPM, revolution per minute, your advancement or your cutting, I don't want to say cutting speed, but the rate at which your tool advances is going to be your feed rate times your RPM. So here we have 0.003 inches, and I'm going to write it like this: per revolution times 400 revolutions per minute. And here's the reason why I'm setting up the units the way I did. The revolutions cancel out. 0.003 times 400 is what, 1.2 inches on top, minutes on bottom. So that's inches per minute. So that means your tool advances at 1.2 inches per minute. Your cutting time. In other words, the time required to make a cut. Let's say we have this tool, we're allowed that 0.003 of an inch per revolution at 400 revolutions. And we need to make a 6-inch cut. So we're going to advance a total of 6 inches. Well, the time required is the length should be L, not 1, length divided by that rate from right there. So we have a 6-inch cut divided by 1.2 inches per minute. So 6 divided by 1.2 is 5. Inches divided by inches per minute is just minutes. So it'd take you 5 minutes to make that cut at that rate. So let's say we're turning a piece. We need to reduce the diameter from 2 inches to 1.75 inches. How much is that reduction in diameter? 0.25 inches. When we are dealing with a lathe, we are not dealing with a reduction in diameter. We need a reduction in radius. Reduction in radius is going to be divided by 2, 0.125. Why do we use reduction in radius? Well, if we're looking at this material, every time we make a pass, right? Let's say that's the material we remove per pass. Notice we've reduced the diameter twice on both ends. So it's easier for us to consider a reduction in radius. So we don't have to consider it once. We don't have to double it. So let's say we have a tool that is capable of removing 0.005 of an inch per pass. That's still 0.005 of an inch per revolution of this material. And let's say we're turning at 200 RPM. So the time it takes to make that reduction. Well, first we got to find that speed. Speed is the 0.005 inches per revolution times 200 revolutions per minute. Revolutions cancel. 0.005 times 200 is what, 1 inch per minute? Does that make sense? So now the time required is equal to the length of that cut, 0.125 inches, divided by the 1 inch per minute. which means we're going to have 0.125 minutes that it takes to cut that. I'm going to assume you guys can make the conversion into seconds from there. So, okay, so we some of the finer tips. Let's look at putting this all together. Let's see, we are looking at a mill. Let's do a 5/8 inch carbide mill. Now I realize with a mill, it does matter whether you're just taking off an edge or if you're cutting a channel down the middle of the material. But again, I'm just going to give you a feed rate. Let's say we're going to need to cut an 8-inch channel. Our feed rate, we're going to allow it to be 0.004, 4 thousandths of an inch per revolution. And we're cutting this in, let's do something a little more. As all of my milling ones have quite a range on them. So let's say that we're cutting this in aluminum. For aluminum, it tells us that our surface cutting speed with carbide mill is anywhere from 500 to 800 feet per minute. So let's pick a number in the middle of that. Let's do 700, works for me. 700 feet per minute. I want to know, how long is this going to take? Now, we're ignoring setup time. We're just looking at cutting the parts. We'll figure in setup time later. First thing we need to find is RPM. N equals 3.82 times our cutting speed over diameter, right? So it's 3.82 times 700 over 5/8. So 3.82 times 700 divided by 5/8. Right. 4278.4. That sucker's flying. True. Now, a lot of times with aluminum, that big range by 5 to 8, it all depends on whether you have pressurized coolant or not. If you have a pressurized coolant, you can push it up closer to the top. Otherwise, a lot of times, a lot of your tools, aluminum will gum up on the tools because it actually starts to melt a little bit from the speed. So that pressurized coolant forces it to stay off the tool. So there's a lot of variables that come in. Let's say we're going to play this on the safe side. We're going to run this at 4,000 RPM. Sound reasonable? So obviously there's a round off error there, but that's fine. So now we're going to look at our advancement speed. Actually, you know what? Let's just do this. We're going to do our cutting time. Our cutting time, our length of the cut was 8 inches, correct? 8 inches. We're going to divide that by our speed, which is the 0.004, the 4 thousandths inches per revolution, times the 4,000 revolutions per minute. So we're going to punch this in the calculator. It's going to be 8 divided by, now there's more than one number on the bottom of this fraction, so again, we must use parentheses, 0.004 times 4,000, and close those parentheses. It gives us 0.5. Now that is going to be in minutes. That's half a minute. So it's a 30-second cutting time. If we need 1,500 pieces, and let's say there is a 1.5 minute setup in between each piece, and 18-minute total setup. That means getting the whole thing set to run to begin with for the whole thing. So each piece is 0.5 minutes to cut it. Come on. It's 0.5 minutes to cut it, plus 1.5 minutes to set it up. So that's 2 minutes per piece. Cutting and setup. Times 1,500 pieces, that's 3,000 minutes. Plus the 18-minute total setup. 3,018 minutes divided by 60, which is what, 50.3? 50.3 minutes. So if I'm bidding this as a job shop, depending on how competitive that bid is, I might bid it as an hour. Or I might try to bid it as 50 minutes to be more competitive, depending on how tight it's going to be. Yes. Yeah, and that's all I did there was just divided by 60 to turn it into, oh, that should be hours, not minutes. Thank you. Hours. Good call. Hours. Yeah. I can squeeze through 3,000 minutes into 50 minutes. Yeah, you're right. It's 50 hours. So, yes, I probably bid that as 50 or 51 hours. Thank you. So, page 45-second setup. So page, I'm going to give you a new pack here. In this new pack, it'll be page 242. Problems 1 through 57, heavy duty odds. I'll get that packet to you right now.